All right, so hopefully you're seeing compound N, which is C5H10O. If you're not seeing compound M, which is C5H10O, well, let me know, and I'll see if I can do something about it. So I should be recording this screen and the audio that goes with it. So we have a spectrum, and we can kind of go through and look at the peaks, but first we ought to calculate degree of unsaturation. That's always the first thing to do. So what would saturated be for C5? And you don't have Isabel, so someone else has to answer now. Anybody? Bueller?
Would it be H12?
It would be, right? 2 times 5 is 10, plus 2 is 12. So C5H12 will be saturated. How many hydrogens do we have? And since there are no halogens or nitrogen, it's just the number of hydrogens, right? So H10. So we're missing 2, which means there's 1 degree of unsaturation. So we can eliminate immediately alkynes and benzene rings. We know those aren't present. We know it's not an ester because there's only 1 oxygen, right? So it certainly can't be an ester. So now we want to start looking at peaks. There's information there above it. Compound M readily decolorizes bromine and carbon tetrachloride and is converted by hydrogen and nickel into compound N, which has a molecular formula C5H12O. That's useful information, but not yet because we haven't done chapter 12 yet. So we don't need that information in order to interpret this spectrum. You'll notice that there's this peak at 0, right? That's the tetramethylsilane standard, and there's this little tiny blip here at 7.2. That's the chloroform solvent. So those are there for a reason. So which peak would we want to look at first, do you think? And generally, it's a good idea to look at simple peaks first. So I'm going to look at this one first. Right? There's a 6 hydrogen singlet. And it's at about 1.3-ish ppm. Why are there 6 hydrogens there? What does that tell me? That there are 6 magnetically equivalent hydrogens.
Would it be 2 methyl groups?
Probably. So I probably have 2 CH3 groups. And what does it tell me that it's a singlet?
Adjacent to 1 hydrogen?
Adjacent to 0 hydrogens, because it's n plus 1 peaks for n adjacent hydrogens. There's only 1 peak, so n plus 1 is equal to 1, which means n is equal to 0. So that means that the carbon that those 2 methyl groups are attached to, they're probably attached to the same carbon, right? That's why they're magnetically equivalent. And that carbon doesn't have any hydrogens. So I can write out CH3-carbon-CH3, and I can just put 2 lines on that center carbon, pointing to something that isn't hydrogen. So that's useful information. I've got 2 methyl groups, and they're attached to a quaternary carbon, where a quaternary carbon is one that has 4 bonds to something that aren't hydrogen. So I've used, in that case, I've actually used 3 of my carbons and 6 of my hydrogens, which means I'm only trying to account now for C2H4O as the rest of the molecule. Right. There aren't very many different ways you can write C2H4O. I've got another singlet here at about 1.9 that's integrating to 1 hydrogen. What does that tell me? Definitely it's a hydrogen, right? And that hydrogen doesn't have any adjacent. And we have an oxygen. And probably that oxygen is not part of the degree of unsaturation. So that 1H singlet at 1.9, whenever you have kind of a 1 hydrogen singlet by itself like that in a molecule that contains oxygen, it's probably a hydroxyl group. So this compound is probably an alcohol. So I can write an OH group there. All right, so now I've used 3 carbons, 7 of the hydrogens, and my oxygen, C3H7O. I'm left with C2H3 that I haven't used yet. And you can see that those 3 hydrogens are down in that region between 5 and 6. Okay. So there are 3 total hydrogens in the region from 5 to 6 ppm. Why are things between 5 and 6 ppm? What does that tell us about the electronic environment of those hydrogens? Between 3 and 4 told us that those were on a carbon adjacent to an electronegative element, but between 5 and 6 tells us something quite different. That should be alkenes. You are correct. So those hydrogens are probably on a carbon-carbon pi bond. And probably they're on the same carbon-carbon pi bond. So we can actually draw what we call a vinyl group, which is a CH2 double bond CH. And you'll notice that the pattern is pretty distinctive. All 3 of those hydrogens are different magnetically, and they're splitting each other. So we have at 6 ppm, we have not a quartet, but a doublet of doublets. All of those peaks are about the same height, so it doesn't follow Pascal's triangle. It's not a 1 to 3 to 3 to 1 ratio, so it actually follows the 2 to the n rule. There are n adjacent hydrogens. There are 2 to the n peaks, and for 2 adjacent hydrogens, that means 4 peaks. And if you look at the other two are doublets, which means they're being split by one thing. That is an ABX pattern, which you'll learn to recognize as a vinyl group, where 2 of the hydrogens are very similar in chemical shift, between about 5 and 5.5 ppm, 5.2 ppm, something like that. Those are the 2 that are on the same carbon, and then the one that's on the different carbon is shifted much further downfield. So the 2 peaks that are around 5 to 5.2 we'd call the A and B hydrogens, and then the one down around 6 we'd call the X hydrogen. Right. The coupling constant, the degree to which the peaks are separated, is different for hydrogens that are trans to each other on a double bond than it is for hydrogens that are cis to each other. So this smaller coupling constant here, the one right around 5, that is the hydrogen that's on the same side of the double bond as the CH group on the vinyl. And this one, that's the trans hydrogen. That's the hydrogen that's actually opposite from the other hydrogen. And then this one here, that's on the alkene that has just 1 hydrogen and is attached to something else. So we've got a vinyl group, CH2 double bond CH, and we've got a carbon that's attached to 2 things that are not hydrogen. we've got an OH group, and we've got two methyl groups. So the likely structure is a CH2 doubly bonded to a CH, and then the carbon that's attached to that has one hydrogen, or sorry, has the hydroxyl group, and then it has the two methyl groups. So what we are probably looking at here is an alkene between carbons 1 and 2, and then carbon 3 has the hydroxyl group and a branched methyl. So we're looking at 3-methyl, 1-butene, 3-ol, right? It's butenol, and the 3 is telling you that it's the alcohol is on carbon 3. So 3-methyl, 1-butene, 3-ol is the structure. We've got that typical ABX pattern. That's a pattern that you'll start to recognize. The carbon NMR, there's actually carbon NMR data there as well. And you see that there are 4 different carbons, right? The 13C NMR, which you probably haven't watched that video yet, but it has 4 peaks. What that tells me is that there are only 4 magnetically different carbons, and that tells me that there must be some symmetry in this molecule. 2 of the carbons have to be the same magnetically. They have to reflect into each other or rotate into each other, because otherwise I should have 5 signals in the carbon NMR, and I don't have 5 carbons. And then if you look at the chemical shift, the 146.12 and the 110.75 ppm, those are the alkene region in the carbon NMR. Right, so that tells me I have 2 carbons that have a double bond. The 71.05, right, that's carbon attached to an electronegative element. So that's the carbon that's attached to the alcohol. In the carbon spectrum, the chloroform, the CHCl3 or CdCl3, that carbon shows up at 77 ppm because it's attached to those 3 electronegative chlorines. Right. In this case, we're attached to an alkene, which is shifting it a little bit down, and we're also attached to an alcohol, 29.38, right? That's just the plain old alkane region. So the carbon NMR actually tells us some useful things. And that information above that says decolorizes bromine and carbon tetrachloride, alkenes react with bromine. They add 2 bromines, 1 on each side. So that tells me it's an alkene, and it's converted by hydrogen and nickel into compound N, which has added 2 hydrogens. That also tells me that the degree of unsaturation is a carbon-carbon or carbon-oxygen pi bond and not a ring, because rings will not be, they won't add hydrogen. So the properties of the catalytic reduction with hydrogen tell me that it's a pi bond rather than a ring. So that's often useful information when you're trying to determine whether degrees of unsaturation are caused by pi bonds or ring. So I've got 3 pages of notes that I wrote out as I was talking through this, and I will scan those and post them along with this video.